Hi everyone, welcome back. In this lesson we're going to talk about the official math terms and symbols that are used to actually express our ideas. So, as we've seen in the past, we've been using diagrams and visualizations to talk about our ideas for how to separate shapes into little pieces. Now we'll actually learn the terminology, which helps us communicate with other people, but also the symbols, which help us write down our equations and ideas and let some of the math begin to do some of the work for us. So eventually we'll have rules that can work on these symbols and we don't have to work as hard. So that's sort of the advantage of going to this format. Now there's sort of a little Rosetta Stone key here, which is sort of taking our concepts and sort of translating them to the words and the symbols. And I'll give you a quick walkthrough now. In the article text there's more examples and details. So the first idea is to kind of sharpen up what we mean by X-rays and time lapses. The official math term is a derivative for the X-ray. So when you have a shape and you want to break it apart, it's called taking the derivative. You're basically taking the whole thing, going along a certain trajectory, and breaking it into slices. And that process is called taking the derivative, and the result is usually the shape that all the slices take. We can either extract out a single slice, which is called taking the derivative at a certain point. So if you imagine a curve like x squared. Now the equation x squared, that can be 1, it can be 4, it can be 9. I mean, it can be pretty much any number, but if we think about the whole numbers, it's 1, 4, 9, 16, 25. That's what the curve can take on. But if we want to talk about the value at x equals 3, well then that's 9. So the derivative is sort of the entire set of all the x-rays, all the pieces, but we can also pull out a single one if we're interested. And so let's talk about it a little bit. Here's a few visualizations. The general format is you say, I want to take the derivative of some shape, so maybe I want to derive the area of a circle with respect to some variable. And that with respect to, that's just basically saying, what's our path through this shape? I mean, we need to go through it somehow. So give me your trajectory that you want to follow as you go through it. So our typical example is we have the rings. We're going to derive the area of a circle, because that's our shape, with respect to the radius, because we're basically following the radius as we go. And the symbol for that is d over dr. And this is basically saying take the derivative with respect to radius of the following shape. And in this case, it's area of a circle. Let's say we wanted the perimeter. Well, we'd say derive the area of a circle with respect to the perimeter, because we're going along the perimeter this time. And so this would be d over dp of area. So if you notice, the order of how we'd say it and how we'd write it is a little bit different. Derive the area of a circle with respect to perimeter. The symbols are really kind of compact, so you sort of get it all at once. So it's d dp of area. And that means we're going around the perimeter. And if we went along the x-axis, we would be d dx. And so if you've seen calculus before, d dx is quite common because oftentimes things are defined in terms of the x-axis, but we don't have to do that. We can take other paths through. It's just that the x-axis is often pretty typical just because that's the way functions are defined. So as you can see, the format is actually pretty similar, right? ddr, ddp, ddx, and each of those is sort of giving us a different path through this shape. And so that's the idea of the derivative. We're taking the x-ray, but we just need two things. One, there's the shaped x-ray, which is in this case the same shape, the area of a circle. And the second is the direction to follow as we do the x-ray. So dr, dp, or dx. So that's the symbols there. Okay, now let's go to the integral. The integral is actually this symbol here, this kind of long S, and it kind of means glue together. So once we have the steps, that's just one part of it, but we actually need to glue them together to get the area. And my analogy here is the derivative is sort of like taking your shape and breaking it apart. You have a Lego set and you kind of take apart all the Legos. Okay, great, you've got all the Legos, but what's a better way to rearrange them and assemble them? That's the integral. So the derivative sort of splits it apart. The integral is actually what measures the result, because we might have this shape here, but we haven't measured the area yet, and that's what the integral does. So we have the little pieces, okay, hey, it looks like a triangle, and we know how to get the area there. So the integral is sort of doing the work of getting the new measurement. That's sort of a subtlety that I missed the first time when I was studying calculus, is the derivative just gives you the pieces. The integral is actually what measures the result and puts them back together. So The way we write this is as follows. We have this kind of symbol here, which means we want to glue things together. We're doing an integral. 0 to r, that's the start and end of where we're gluing things together. So if you notice, on this shape, we're going to start at the very beginning of the radius at 0 and go all the way to the max value, which is r. And then the thing inside here, 2 pi r, that's called the integrand. That's basically the shape that we're going to start gluing together. So if you notice, each of these is a little unrolled ring. It's a rectangle. The height is 2 pi r, and the width is dr. Now this is where it gets a little bit tricky. Let's scroll up here to the top. For each of these steps, the height is 2 times pi times r, and the r is actually the current value of the radius when we're at a certain segment. So if you imagine we're taking a radius, dividing it into little steps of size dr, so that's our step. Each step, there is a value of the radius. And so this is kind of a subtlety here. When we have an r in the context of an integrand, in the context of something being integrated, the value of the variable is actually the value at that step. Because r, when we look at this equation, we think of r as the very last one, but in this case, it's actually the value of r at our current step. I wish there was different notation. It would be nice if it was r with a sub dr, so we knew that it was really referring to this step, but the notation is really concise, and there's a lot of implicit assumptions there. So when we come back down here, oops, all the way here, this equation here is saying, okay, we're going to go from 0 to r, from the center to the full radius, and along the way we're going to add up these little strips. Each strip is going to have 2 times pi times r. That'll be the height of the strip, and dr wide. So each strip is dr wide, and 2 pi r is kind of how tall it is. Again, this r is referring to the value of the radius at that strip. Whew. That is a much more involved and intricate way to put things, but it's very compact at the same time. Now, we don't have to be so specific. We can actually say, well, we want to add up some pizza slices, and we haven't actually specified how big it is. We can do that as a kind of follow-up question, but we can just get an idea for what the integral should look like. So we start at some minimum value, we go to some max value for the perimeter, and along the way we're adding up these pizza slices. Now the pizza slices are a certain amount wide, dp wide, and they have a certain kind of area as a result. And so the idea is to say, okay, well, let's just write it out, and then eventually we will put the area together. And the same thing for the board. So we can say, okay, we're going to go from a min x value to a max x value. And along the way, we have these boards to add up. The board is dx wide, that little dx piece, and it's got some height that we need to measure. So these symbols are really compact. This is how we'd write it out in kind of a formal description. And that's really lengthy. It's like saying is equals to. We want to have little symbols that kind of shorten things up for us because the rules will be easier to read and a little bit easier to work with in that way. So this is sort of the high-level description of calculus. There's a few symbols there. We can always turn it back into English, but there's a sort of formal notation that once we get the hang of it, it'll actually make working with calculus a little bit easier.